All right, let's look at our second part of lecture 6. Now, a lot of times when we have a redox reaction, it's going to occur in a couple of different ways. One way is when your reducing agent is in direct contact with an oxidizing agent, so that we have our two reactants in direct contact with each other. And when that happens, the electrons are transferred directly from one species to another. So in this example, we see that the zinc and the copper collide, and the electrons are transferred from the zinc to the copper there. And so that's one way to do it. And in this case, since the copper solution was reduced, going from copper 2 plus to copper, it is the oxidizing agent. That can be a little confusing. And since the zinc was oxidized, that is the reducing agent. And so when we say that something is an agent, what we're talking about is not what happened to it, but what it did to something else. So since the copper was reduced, it made the zinc get oxidized, and so it's an oxidizing agent. And here, since the zinc was oxidized, it made something else get reduced, and so it is the reducing agent. It can be a little confusing. You just have to remember that those two things are opposite because we're taking an opposite point of view. What happened to it versus what did it do to something else? So anyways, back to this one. So when we have our two agents in contact with each other, those electrons are transferred spontaneously and very quickly from one atom to another. Now, if we look at our common batteries, they're actually descendants of galvanic cells. And our galvanic cells are a spontaneous electrochemical reaction where the electrons flow once we have a complete circuit. So just like you think of a complete electrical circuit, the same holds true here. You have to have a flow of charge in order for a circuit to be closed and in order for a reaction to occur. Now, what we can do with our batteries, rather than put like a piece of zinc into a copper solution, we can actually separate these components and have a setup where we allow the electrons that are being transferred to go through an external circuit and something conductive, such as a wire. And we're going to look at this here in just a little bit later. So the type of cells that we're looking at here are galvanic cells. They are also called voltaic cells. Those two terms are interchangeable. They mean the exact same thing. Okay, so when we have a voltaic or a galvanic cell, what that means is that primarily is that our reaction will happen spontaneously. The electrons will flow spontaneously when our circuit is complete. And so what we're going to do with these cells is we're going to separate our two half reactions physically, like in two separate beakers. And what that will allow us to do is to hook those two half reactions together through an external circuit, and that's where the electrons will flow, and we'll be able to do some kind of electrical work with those electrons in that external circuit. So once that circuit is completed, because we have a voltaic cell, we have a spontaneous electrochemical reaction. Electrons will begin to be transferred, and they will flow through the wire. So here's an example, and I'm going to be doing a lot of drawing here and a lot of annotating, so just bear with me. So here we have a lot of different things. We have our zinc and our copper pieces of metal, and so we have both zinc metal and our zinc solution ion there. And in the other beaker, we have our copper ion and our copper metal. Since we know that the zinc is losing the electrons, we can think of our electrons flowing out of the zinc and flowing into the copper there. So they run that way through an external circuit, and there we see that we're lighting a little light bulb up right there. So that's where we have what we have happening there. Notice in our oxidation site, the electrons that we see flowing are coming from zinc atoms present in that metal. Now, let me get a different color there. bright red. So there we go. So we've got that zinc atom there. When it loses 2 electrons, it becomes a zinc 2+ ion, and zinc 2+ ions cannot hang out with the zinc atoms that they used to be buds with, and instead they get ejected from the metal surface and they go out into the solution. And so what you start to see over time with your zinc metal is it would start to corrode and start to get eaten away, and so eventually it just might look something like that. It would be really eaten away there and eroded. So over on this other side, we've got reduction taking place, and you can see that the electrons come down through the wire down into the copper metal, and when they come in contact with a copper ion in solution, if there's a copper ion contacting the metal electrode there, and the electrons can grab onto that, then it gets reduced and becomes a copper metal atom, and it gets deposited on the metal surface. And so over time, what happens with this electrode is it starts to get a little bit bulky as copper metal builds up on it, because you have reduction taking place there. Now, some other things that we want to take a look at is the signs on our electrodes. Just like when you have a battery, you have a plus side and a minus side, and when you're putting your batteries into a device, you have to make sure that they're going in the right side, or the right way, I should say. And so where the electrons are coming out of is a negative charge, and so we call that the anode. Just like a negative ion is an anion, a negative electrode is an anode. And which way do they go? Well, the way I like to think of it is electrons are attracted to positive things because they're a negative charge, and so electrons flow from anode to cathode. They flow away from the negative sign and towards the positive sign. And so we have our positive electrode there. So a positive ion is a cation, and so a positive electrode is a cathode. And so that's what our copper is. You also have anode is always the site of oxidation, and your cathode is always the site of reduction in a galvanic cell. Okay, so those two things never change. And some of you may have heard the phrase an ox and a red cat. To me, it always sounds like the start of some weird fairy tale that never went anywhere. An ox and a red cat went down the road to buy something, I don't know. Make up a poem if you want, but an ox and a red cat tells you that you have an anode, an oxidation, reduction at the cathode. So those are the two parts that you need to remember there. Let's see, I think that's the main thing for that. The other thing I want to talk about, we're going to talk about this in a little bit more detail here later, but since we have the picture, I want to discuss it now. This idea of the salt bridge. So the salt bridge here is a connecting feature in your battery, and it holds an electrolyte in there, normally at a very high concentration. What the electrolyte does is it maintains a constant flow throughout the battery, so you have a complete circuit, and it also makes sure to replace charge that's lost or neutralize charge that's gained. And so if we look at the solution over here on the left, our zinc solution, as the reaction proceeds, we are pumping zinc 2+ ions into that solution. So we are increasing the amount of positive charge in the solution. All solutions have to be neutral. And so what the salt bridge does is it starts dumping negative ions into that solution. So that for every zinc ion that gets oxidized and put into the solution, the salt bridge pumps 2 nitrate ions into that solution as well to maintain charge neutrality. Over here on the reduction side, the right-hand side, we have your copper ions being lost from the solution because they're turning into copper atoms. And so positive charge is being lost, and so the salt bridge responds by dumping positive ions into that solution as well. You'll notice that the two ions involved here are nitrate and potassium, two very non-reactive ions. They're not going to precipitate with anything. They're not going to react with anything, and that's good. We don't want them doing that. We just need them there for the charge. And we need to put them in a really high concentration so that they don't run out, because if one of those ions runs out, then the battery's going to stop because it won't be able to maintain a charge neutrality. So all kinds of different parts and pieces going on in this voltaic cell. So again, I mentioned we're going to talk about the salt bridge, and I didn't realize it was the next slide, but here we are. So I mentioned it plays a couple of important roles. One is it completes the circuit. It allows for a constant flow of charge. We saw that the negative charge of the electrons going from left to right in the external circuit, and then if you followed the charge, the negative charge, through the salt bridge, it went from right to left, and so you have a nice circular flow in your battery there, constant flow of charge. We also saw that it balances the charges in the solutions so that you never have an imbalance of charge within those solutions, because if they get an imbalance of charge, the battery will stop. Okay, so here's an example. I want to describe this cell with this reaction here. So we've got iron goes to iron 2+, and copper 2+ going to copper metal. And this is something that I'd like you to try to do, some things I want you to try to label. I want you to draw the cell, label the anode, the cathode, identify the site of reduction, and oxidation, positive or negative electrodes, direction of electron flow, and the interaction of the salt bridge with that circuit as well. So go ahead and try to identify those things there, and I will have that posted as a separate video on YouTube. So if we had to describe an electrochemical reaction by drawing that battery, hopefully like you just did, every single time we wanted to refer to some kind of electrochemical reaction, it would be a little bit tedious. And so we use something that's called cell notation that helps us describe the exact same cell as one of those diagrams that we just did. And so if we go back to our copper and zinc cell, this is the way that we would write that cell in cell notation. Now there's all kinds of different parts and pieces. We're going to talk about each one here. So our anode, by definition, in cell notation, will always go on the left-hand side. Okay, so we saw that our zinc was the anode, and notice that we've got zinc on the outside and zinc 2+, because when we read our reaction in the anode, we have that species being oxidized, and so when reading right to left, we go from reactants to products. So the reactant in our electrochemical reaction was zinc turning to zinc 2+. Okay, so that's our anode. We've got its form. We got zinc 2+ in aqueous. That's not always written there because sometimes that's very obvious. And something else that we have here is the concentration. That's not always shown either. Occasionally it is, occasionally it's not. If it's important, it's certainly going to be shown. Sometimes it's not really important, so it doesn't get shown. On the right-hand side, we have our cathode there. And notice again that cathode is our site of reduction, so we have something gaining electrons. And so we had copper 2+ turning into copper, and so we have things in the same order here going left to right. So copper 2+, again, we have the aqueous and the concentration at 1 molar there, which isn't terribly important. Sometimes that shows up, sometimes it doesn't. And then we have our electrode there at copper. So notice that we also have some interesting lines there. Okay, we've got those straight up lines, we call them pipes. Okay, so there's one right there, and there's one right there. Okay, anywhere that we see those vertical lines in our phased in our electrochemical cell notation, that means that there's a phase boundary. Okay, so our zinc here is solid, our zinc 2 plus here is aqueous, and the copper, our copper is aqueous, and our copper here is a piece of metal. So we have a separate phase. And then we also have those two lines right in the middle there. And that represents our salt bridge. That represents a physical barrier between the species, between the zinc 2 plus and the copper 2 plus. It tells us that they are not in contact with each other, and that's where the salt bridge goes. Okay, so here's an example that we can try. We see that the cadmium species is what's being oxidized because we went from cadmium 0 charge to a cadmium 2 plus charge. So to do that, it had to lose electrons to do that. The nickel went from nickel 2 plus to nickel solid, and so that had to gain electrons. Okay, and so losing electrons is oxidation, and oxidation happens at the anode. So that's where we want to go for our first cell notation. So we're going to have cadmium solid, then we're going to have our phase boundary, and then cadmium 2 plus aqueous. Okay, and that's all we know. We don't know the concentration, so we don't need to put it in there. Okay, then we have our salt bridge. Okay, and then our reduction side, we're going to have nickel 2 plus aqueous, and then we have a phase boundary, and then we have nickel solid. So that's all there is to writing out the cell notation for that electrochemical reaction. Pretty easy to do, much easier than drawing out an entire battery. Now, the reason we need to put in our phase boundaries and sometimes the actual phases of the electrodes that are in there is because sometimes you'll have an aqueous and an aqueous situation, or sometimes you may even have a gas species used in the electrochemical reaction. So you do have lots of different phases. It's not always just an aqueous ion and a solid. Lots of different types of electrodes, electrode situations exist. So when you have a gas species is either your reactant or a product, we need an electrode that can either take the electrons or bring the electrons to the desired reactant or from the desired product, but we don't want that electrode to get involved in the reaction itself, because that would change the chemistry of the reaction that you're looking at. So one of the more common materials is platinum. Platinum is one type of inert electrode. Inert means it doesn't react. And platinum is one of the coin metals. It's like gold. They're very non-reactive. They do not give away their electrons easily at all. So for the most part, nothing reacts with them. And so sometimes you will see gold electrodes as well. Mercury is also used occasionally. You'd actually use a drop of mercury, and you would react on the surface of it. When the surface of it gets too cruddied up from other things, you just hit a little button and the liquid just spits it out, and it brings a brand new drop in there. So it's kind of neat. So platinum, gold, mercury, very common for inert electrodes. And again, the reason we use these is that these metals are very unreactive in electrochemical situations. They can't be used in every situation because there is a way to react with platinum, gold, and mercury, but for most of the reactions that are done, they work very well. Now, one of the most common electrodes that we use these inert electrodes for is the standard hydrogen electrode, or you see it abbreviated a lot as the SHE. And that electrode is important. You don't see it very often. I personally have never seen one, but it's a very important electrode because it is the voltage reference for all electrochemical reactions. It's kind of like what sea level is to all of our elevations that we find on a map. Our maps have elevations, but there has to be a 0 point, and so sea level is chosen as that 0 point. And we had to do that for voltage references as well. And so we chose the standard hydrogen electrode to be our sea level. So here's an example of a standard hydrogen electrode. We've got platinum electrode here. It's usually something that's called mossy platinum, or it might be platinum foil, or it might be a platinum mesh. It can be all kinds of different forms of platinum. But we have a 1 molar acid solution here. It does have to be 1 molar for standard conditions. We have our H2 gas being pumped in here, so this is sealed where the wire comes in. It's platinum wire. So the hydrogen comes in, it comes down, it bubbles over the platinum, and it exchanges electrons in equilibrium between the acid and the gas. And so there's all kinds of exchanges of electrons there. But that gas has to be at 1 atmosphere as well in order to be under standard conditions.